All right, so today we will be attempting to cover section 7.2 and section 7.3. That may seem like a lot, but the topics are kind of related to each other. And it's just, it all has to do with the sampling distributions that we started talking about last week with section 7.1, and dealing with sample proportions, p hat, and sample means, the x bar, and how to deal with those within our sampling distributions. So that's what we're going to do today. Hopefully this will make sense. I've got some examples set up. I tried to take those like pre-made slides that I have been using from the textbook people and kind of pare it down into a single presentation. Hopefully that works. There'll be, I think, to try to make it a little more efficient for us today, there's going to be a few spots where I specifically say you should probably write things down as far as like formulas and rules for those formulas. Other than that, if you have a question and you need me to slow down, please tell me to do so. But the other parts of the presentation are just to help make sense and to introduce these formulas and rules. So that's kind of the general idea for today. So just to try to make time a little bit more efficient and to help you guys know what things you need from the presentation as far as your notes go. So hopefully this works. Yeah, so there's that. So we're gonna get going with that. And yeah, so here we go. Let me start by sharing my screen. That helps. That's the one I want. There's that. All right, so here we go. 7.2 and 7.3 sample proportions, that's section 7.2, and sample means, that's 7.3. And this is all part of chapter 7, sampling distributions. All right, so our learning objectives today is to find the mean and standard deviation of the sampling distribution of a sample proportion or a sample mean. We need to check the 10% condition before calculating the standard deviation of sample proportions or sample means. The 10% condition applies to both, and that's making sure that the sample is not larger than 10% of your population. We're going to determine if the sampling distribution of sample proportions is approximately normal. There's a special condition attached to that. We're going to explain how the shape of the sampling distribution of a sample mean is affected by the shape of the population distribution and the sample size. And if appropriate, use a normal distribution to calculate probabilities involving sample proportion and or sample mean. Right, so the normal distribution calculations are not going anywhere. If you are not comfortable with those yet, you need to practice. You need to try to do problems that involve that. Okay, so these are our objectives for today. So sample proportions, the sampling distribution of P. So we're starting with sampling with sample proportions. That's the first half of this lesson. So how good is the statistic p hat as an estimate of the parameter P? Sampling distribution of p hat answers this question. Remember we talked about in our previous lesson that we want an unbiased estimator. All right, consider the approximate sampling distributions generated by a simulation in which SRSs of Reese's Pieces are drawn from a population whose proportion of orange candies is either 0.45 or 0.15. So we've got two separate populations set up. And we're going to consider what do we notice about the shape, center, and spread of each. So first we have a sample of Reese's Pieces with a population proportion of orange of 0.45. And we get this distribution. We have a sample size of 25, and we see that the center is approximately 0.45. We actually get the p hat of 0.48, we increase the sample size to 50, right? We get a little less variance. And again, the proportion for the population is 0.45, and p hat ends up being 0.46, but still our center is a really good estimator here. We're pretty close. So those are our sampling distributions for 0.45. If we go to the 0.15 distribution, right, we still get two distributions that are relatively close. Right, so now these are a population with 0.15 orange Reese's Pieces, right? And we still have the center of our distributions pretty close to the actual proportion. Obviously, as we get a larger sample size, we get less spread and a little bit more accurate p hat than we did in the smaller sample size. All right, so viewing the distribution helps us answer, is the statistic a good estimate of our parameter? So these observations tell us that the shape, in some cases, the sampling distribution of p hat can be approximated by a normal curve. If we look at those four graphs, those graphs looked mostly approximately normal, right? This seems to depend on both the sample size n and the population proportion p. The center, the mean of the distribution, is mu of p hat equals p. This makes sense because the sample proportion p hat is an unbiased estimator. Right? So this is kind of nice. The mean of the distribution of our sampling distribution is equal to whatever the proportion was, right? Our parameter. For a specific value of p, right, that's our parameter p, the standard deviation, right, of p hat gets smaller as n gets larger, right? We get less variance, and that's again what we talked about in the previous lesson. As we get a larger sample size, our sampling distribution gets narrower. There's less variance. The value of the standard deviation of p hat depends on both n and p. Right, so again, the shape depends on n and p, sample size, population proportion. Standard deviation also depends on the sample size and the population proportion. So there's an important connection between the sample proportion p hat and the number of successes x in the sample. All right, so essentially with the orange candies of Reese's Pieces, we're using the random variable x to equal the number of orange candies in the sample, and we divided that by the sample size, and we got p hat, right? The proportion of orange candies. You don't need to write this formula down. We deal with this formula in a moment. Is there any questions so far? So in chapter 6, we learned that the mean and standard deviation of a binomial or random variable, x, are the mean of x, right? Random variable x is n times p. Standard deviation of x is equal to the square root of np times 1 minus p. Since p hat equals random variable x divided by n, which is equal to 1 over n times x, we are just multiplying the random variable x by a constant 1 over n to get the random variable p hat. Right? Therefore, the mean of p hat is 1 over n times np, which is just equal to p. So p hat is an unbiased estimator of p. And the standard deviation, so again, we're using the formulas from a binomial random variable. Right? And we're doing essentially a linear transformation by multiplying by a constant. So the standard deviation of p hat is 1 over n times standard deviation of the random variable and we end up with the square root of p times 1 minus p divided by n. Right. As sample size increases, the spread decreases. Right. So this is just kind of explaining how we come up with the two formulas that we will formalize on the next slide for calculating sample proportions, sample means, or sampling distribution of p hat, right, or sample proportions. Bleh, sorry. So the next slide is where you're going to want to take notes for your notes. So the sampling distribution of a sample proportion. If we choose an SRS of size n from a population size capital N with proportion p of success, then we let p hat be the sample proportion of successes. Then the mean of the sampling distribution is p hat is the mean of p hat equals p. There's literally no calculation that you have to do for that. You just have to copy down the parameter from the original population. Right, so the mean of sampling distribution of p hat is p. The standard deviation of the sampling distribution of p hat is the square root of p, probability of success, or the proportion of successes, times the proportion of not successes, 1 minus p. Right, so these two things that you're multiplying should add up to 1. Right, so if you have 0.45 orange candies, that's a success. Then you have 0.55 not orange candies, that would be the 1 minus p. You multiply them together, divide by the number, the size of your simple random sample, right? And then you take the square root of that number, and that's our standard deviation. The standard deviation can only be calculated as long as the 10% condition is satisfied. And again, you need to make sure that the sample size is less than or equal to 10% of your population size. And you can either do the calculation if you know exactly the population size, or you can generally say, well, it's obvious that our sample size is less than 10% of the population, depending on population you're referring to. As n increases, the sampling distribution becomes approximately normal. Before you perform normal calculations, check that the normal condition is satisfied. All right. And this normal condition, this is the large counts condition. We need to make sure that basically the number of successes is greater than or equal to 10, and the number of failures is greater than or equal to 10. Right? This condition only applies to sample proportions when we're talking about sampling distributions. Right? We have to check that large counts condition. So these are the formulas we need. See, we need a moment to write any of this down for their notes. Please raise your hand. All right. All right, so now we're going to look at some examples. So here we go. So this is our example for sample proportions. So we have about 75% of young adult internet users, age 18 to 29, watch online videos. Suppose that a sample survey contacts an SRS of 1,000 young adult internet users and calculates the proportion p hat in the sample who watch online videos. All right, so we have 75%. Right. This would be p. Right. We have an SRS of 1,000. Right. That's n. That's our sample size. Right. So we have to calculate number one. What's the mean? Well, the mean is kind of the easier one to do. The mean of p hat is equal to p, which is equal to 0.75. That's it. That's the whole calculation. So the mean, right, is that one. Standard deviation, remember, before I can do the standard deviation, I need to verify 10% condition has been met. We have 1,000 young adult internet users. We can say that essentially 1,000 is less than 10% of all young adult internet users. So the 10% condition is satisfied. Right, so that's good. So then we can do our calculation for the standard deviation. Standard deviation of p hat is equal to the square root of 0.75 times 0.25 divided by 1,000. Right, which is, there it is, 0.0137. Right, so now we have our mean and standard deviation. Right, so essentially it's that about 75% of our users, of the young adult internet users, watch videos, and we will typically have a variance of about 0.137 from the mean of some of these randomly selected users. So now let's move on to number two. All right, number two is check the large counts condition. Is the sampling distribution of p hat approximately normal? So again, the large counts condition says that I have more than greater than or equal to 10 successes and greater than or equal to 10 failures. So we just need to confirm that that holds, that that's true. Right, so that means we have to do 1,000 times 0.75, which equals 750. And that is more than 10. And if we do 1,000 times 0.25, that equals 250, which is also more than 10. Excellent. So that means the sampling distribution of p hat is approximately normal. So that's question number 2. Our last question, if the sample size were 9,000 instead of 1,000, how would this change the sampling distribution of P? All right, well, the mean won't change. That's not dependent on the SRS. It's only dependent on the proportion from the population. All right, so for number 3, the sampling distribution will be approximately normal with the mean equaling 0.75 still. But the standard deviation is going to change. All right. And it will actually decrease by a factor of 3. Right? And we get that because 9,000 is 9 times as large as 1,000. But since we're doing the square root of 9 is 3. So it decreases by a factor of 3. And so we get the standard deviation, 0.75 times 0.25 over 9,000, and we get 0.0046 as our new standard deviation. All right. So this is kind of how we get to use those 2 new formulas and our new knowledge and understanding. All right. Is there any questions about the example? Is there anything I can clarify? The 0.25 is 1 minus P. All right, so the 0.25 here, remember our, so here, so this 0.25, this part right here is 1 minus P. Is our standard deviation formula is P times 1 minus P over N. Right. So that's what I was saying earlier. These 2 numbers, the 0.75 and the 0.25, they need to add up to 1. So whatever your sample, or not your sample, whatever your population proportion is, right? P, that's that parameter, goes in, it's one of them, and then its complement to make it equal to 1 is 1 minus P, right? So those 2 things have to add up to 1. Does that answer your question, Wesley? Sweet. Any other questions? Anything else I can clarify? Does anyone need a moment to write anything down from the example, or do you need me to like scroll or anything to see something? Okay. All right, so then back to our presentation. And don't worry, this will be posted for you guys as well. So next, that's sample proportions. Now we're going to move on to sample means. So now we're going from p hat to x bar. Right. When we record quantitative variables, we are interested in other statistics such as the median or mean or standard deviation. Sample means are among the most common statistics. Consider the mean household earnings for samples of size 100. Compare the population distribution on the left with the sampling distribution on the right. What do we notice about the shape, center, and spread? So we have our population distribution. Right, so we have the household earnings. This is a population. It's somewhat skewed to the right. However, if we do the mean household earnings for samples of size 100, right, with a sample size of sample size 100, we get something that looks a lot more normal. Right, and right, we get, because both histograms use the same scales, we can directly compare this with the histogram at the left. Right. So rather than percent of households, we're doing percent of samples. Right, we get this much more normal looking, much taller, less varied distribution. Okay. So the sampling distribution, I guess in terms of statistics, behaves better because we can call it approximately normal and we can do a lot more stuff with it. Excuse me. When we choose many SRSs from a population, the sampling distribution of the sample mean is centered at the population mean mu and is less spread out than the population distribution. And that's what we just saw. Right, if we go back, right, we have the mean here. Basically, the same mean occurs here. Right, so that's kind of nice. All right, so then this is what you want in your notes. The sampling distribution of a sample mean. Suppose that x bar is the mean of an SRS of size n, drawn from a large population with mean mu and standard deviation sigma. Then the mean of the sampling distribution of x bar is mu. So once again, there's no calculation. Because this is an unbiased statistic, I just get to take the mean from the population and say that that's the mean of my sampling distribution. Very nice, right? No calculation, just transfers over. The standard deviation of the sampling distribution of x bar is sigma divided by the square root of n. So again, I just get to use the standard deviation from the population divided by the square root of my sample size. Once again, the standard deviation depends on the 10% condition being satisfied. Right? So again, that means we need to check the 10% condition before being able to calculate the standard deviation. If the 10% condition fails, then I cannot calculate the standard deviation, which means I can't do normal approximations and things like that. Sorry, there's people like knocking on my roof here. I keep hearing it. All right. So there's that. No, these facts about the mean and standard deviation of x bar are true no matter what shape the population distribution has. Right? We can have a skewed distribution, right? A crazy looking distribution. Doesn't matter for the population. All right. These things still work. So that's comforting. All right. Does anyone need a moment to write anything down from this slide? Please raise your hand. So sampling from a normal population. We have described the mean and standard deviation of the sampling distribution of the sample mean x bar, but not its shape. It's because the shape of the distribution of x bar depends on the shape of the population distribution. In one important case, there's a simple relationship between the two distributions. If the population is normal, if the population distribution is normal, then so is the sampling distribution of x bar. Right? This is true no matter what the sample size is. Right? So if our population is normal, sampling distribution will be normal for x bar, no matter what sample size. Right? Previously, we saw that the sample size can essentially adjust things from not normal to normal. So we have this sampling distribution of a sample mean from a normal population. Right. Suppose that a population is normally distributed with mean mu and standard deviation sigma, then the sampling distribution of x bar has the normal distribution with mean and standard deviation sigma divided by square root of n. Right. Same formula we saw on the previous screen, provided that the 10% condition is met. Okay. So this is nice, right? This works. Things are normal that start normal, they stay normal, and that's good. All right. So then, if you need a moment to write anything down, can you please raise your hand? So now we're going to look at an example. So then, second. All right. So we have the length of human pregnancies from conception to birth varies according to a distribution that is approximately normal. The mean 266 days and standard deviation of 16 days. Right, so we have our mean and standard deviation from the population. And we have that this is normal, so that's always nice. So now, question number one. Well, suppose we choose an SRS of 6 pregnant women. We're going to let X equal the mean pregnancy length for the sample. Right, so this is N. We need to calculate the mean and standard deviation of the sampling distribution of X. So first, we have the mean of X bar. Actually, I need a fancy X. All right, that will just be equal to the mean, which is 266 days. Yay. Now, we need to find standard deviation, but again, we need to confirm the 10% condition is met. Right? Well, 6, right? The sample size of 6 is less than 10% of all pregnant women. So standard deviation of X bar is equal to sigma divided by the square root of n, which is 16 divided by the square root of 6. And we get approximately 6.532 days. And that should say days. All right. So again, I can't really calculate to a specific number. We just know that 6 is definitely less than 10% of all possible pregnant women. So we just kind of state that and say, okay, 10% condition is good. We can do our calculation. Oop, too easy. So then we can move on to question number 2. And find the probability that the mean pregnancy length for the women in the sample exceeds 270 days. So then we are finding the probability, right, that X bar is greater than 270. So that involves now doing a normal calculation, right? So we need to standardize 270 based on the mean and standard deviation that we just calculated. So we calculate Z is 270 minus 266 divided by our standard deviation we just calculated, 6.532, and that gets us about 0.61. Right? Because of the amount of decimal places we can actually use in table A, there's no need to keep more than 2 decimal places when we get the standardized score. Right? So then that means that this is equal to the probability of Z being greater than 0.61, which remember, table A only gives us less than or equal to values, so we use the complement rule. That is equal to the probability of 1 minus P being less than or equal to 0.61. So we look up 0.61 on our table A, which I don't have pulled up here, but that's what we did. And we end up with 0.2709, right? Which means that there is a 0.2709 probability that when selecting 6 random pregnant women, that their pregnancy length exceeds 270 days. Right. And that answers our question. Is there anything I can clarify with this example? Does anyone need a moment to write anything down? So I'm going to jump back into here. So then, continuing with our sample means, we have the central limit theorem. Right? Most population distributions are not normal. Right? What is the shape and sampling distribution of sample means when the population distribution isn't normal? Well, It is a remarkable fact that as the sample size increases, the distribution of sample means changes its shape. It looks less like that of the population and more like a normal distribution. Right? When the sample is large enough, the distribution of sample means is very close to normal, no matter what shape the population distribution has, as long as the population has a finite standard deviation. So you need to have a standard deviation for your population for this to work. Right? So if we draw an SRS of size n from any population with mean mu and finite standard deviation sigma, the central limit theorem, CLT, says that when n is large, the sampling distribution of the sample mean x bar is approximately normal. Right? Again, this is excellent news. Because now, even if our population isn't normal, if our SRS is large enough, we can do normal calculations. And we'll define what large enough is in a moment. So we need a moment to write anything down. So even when the population distribution is very non-normal, the sampling distribution of the sample mean often looks approximately normal with sample sizes as small as n equals 25. Right? Often, not always. So we get this normal large condition for sample means. Right? If the population distribution is normal, then so is the sampling distribution of x bar. This is true no matter what the sample size n is. If the population distribution is not normal, the central limit theorem tells us that the sampling distribution of x bar will be approximately normal in most cases if n is greater than or equal to 30, meaning our SRS, our sample size, is 30 or more. If we have this condition, then we can use normal approximations for doing calculations for that statistic. The central limit theorem allows us to use normal probability calculations to answer questions about sample means from many observations, even when the population distribution is not normal. And so this kind of lets us know why we have these random variables and these sample statistics, sampling distributions. It's because it allows us to filter things into calculations we can do, no matter what our population looks like. Right. And so again, this right here in the little colored box is something you should have in your notes. Right. The normal large condition for sample means. Does anyone need a moment to write anything down? So in a nutshell, right, proportions versus means. When we're talking about sampling distributions, right? Sample proportions, you have a mean that is equal to the population proportion. Standard deviation is equal to the square root of the population proportion, the parameter p, times 1 minus p divided by n. Right, 10% condition must be satisfied to find the standard deviation for a sample proportion. As n increases, the sampling distribution becomes approximately normal, so you need to check the large counts condition, all right, to do normal calculations, meaning that the number of successes needs to be greater than or equal to 10 and the number of failures needs to be greater than or equal to 10. Then you can use normal calculations. When it comes to sample means, right, the mean of x bar is equal to the mean of the population, and the standard deviation of x bar is equal to the standard deviation divided by the square root of the sample size, n. And again, for the standard deviation, the 10% condition must be satisfied. Right? So it's always good just to check the 10% condition when you're dealing with sampling distributions. If the population distribution is normal, then so is the sampling distribution of x bar. And then the central limit theorem says that when n is large, greater than or equal to 30, the sampling distribution of the sample mean x bar is also approximately normal. This kind of puts it all in a nutshell here, side by side. Does anyone have any questions or need clarification on these things here? Does anyone need a moment to write anything down? All right, so in summary, we can now find the mean and standard deviation of the sampling distribution of a sample proportion or sample mean. We know that we need to check the 10% condition before calculating standard deviation of sample proportions or sample means. We determine the sampling distribution of sample proportions. If the sample distribution of sample proportion is approximately normal, we have to check the large counts condition. We can explain how the shape of the sampling distribution of a sample mean is affected by the shape of the population distribution of the sample and the sample size, meaning if the population is approximately normal, then so is the sample mean. If the population is not approximately normal, then with a large enough sample size, the sample mean becomes normal, right? Greater than or equal to 30. If appropriate, we can use the normal distribution to calculate probabilities involving sample proportion or sample mean. Again, that is standardizing scores and using table A and calculating probabilities in that manner, as long as we're allowed to, as long as the distribution is normal. All right. Is there anything you would like to take a look back at or anything I can clarify from this presentation or the examples? Excellent. All right, so that was section 7.2 and 7.3. So that essentially wraps up chapter 7 on sampling distributions. Obviously tomorrow in class, we will do practice with our sampling distributions, sample means, sample proportions. So please make sure you're here for that because that'll be excellent. I also do encourage you to please take a look at the practice problems. I'm hopefully going to be able to post the solutions to all the practice problems for chapter 7 later this week, so you can check your work. But those are also excellent opportunities to practice this content. And other than that, that is all we have for today. So if there's anything else I can help you with, please stick around and ask, or send me an email. Other than that, I will see you guys tomorrow. Same bat time, same bat channel. Have a lovely day, and we'll see you later.